Winkleblack. This is Trevor, DeVore. We're going to be presenting, as was already mentioned, a heterogeneous defeat solution to genetic selection related analysis. Also here is one of our co-authors, Dr. Trevor. This research actually came out of our theses that we did at California Polytechnic State University, also known as Cal Poly San Luis Obispo. We both have a computer science background, so we didn't really have much of any way of training in terms of bioinformatics. We were approached by the dairy science department. They had an issue, they had an application that they were using to optimize milk production in dairy cows. And so they wanted to make it faster, but they weren't quite sure how to go about that. So they came to us, and that's really where this project evolved from. So the application that they brought to us is called GenCell. And what GenCell does is for any genotype group of individuals that has a set of observable traits, you can then optimize for that set of traits. And from that, then you can get an estimated breeding value for that group of individuals. The problem that they were trying to solve is that it was computationally expensive and as a result very time consuming. And it was only going to get worse. So currently, one analysis is done on about 50,000 markers with about 200,000 observations per marker. And in the next few years, we're seeing that trend toward about 1 billion observations per marker. So that's going to dramatically increase the computation time. So a little bit of background. GenCell performs this analysis using Bayesian inference, but because Bayesian inference is difficult to implement directly because there's no closed form solution guaranteed, and in the cases where there is a solution it's pretty much infeasible to do in a reasonable time frame, we use Gibbs sampling. Gibbs sampling allows you to empirically create the posterior distribution by doing a lot of random mixing and converging upon the expected value. That's also not without its challenges because you need to have this random mixing and converge upon your desired values. You have to go through tens of thousands of iterations. In our case, we did about 50,000 iterations throughout this process. So Gibbs sampling belongs to Markov chain Monte Carlo methods, which, as you probably are aware, are kind of inherently iterative. So they have memoryless transitions from one state to the next, and the next state only depends on the current state. So you can't really break up each iteration and perform them independently. They need to be performed sequentially, which makes it problematic for using parallelization as an optimization tool. Nonetheless, we did it anyways using a heterogeneous compute environment. So heterogeneous computing is the combination of multiple computing paradigms to get the best of both worlds. In our case, what we used was a standard CPU computing paradigm as well combined with GPU computing. So CPU computing is your standard central processing unit that you have powering your general tower. This type of processor is optimized to reduce latency, and it does that by having a high clock speed, a few number of threads that can do tasks independently, and can be switched out very frequently. Newer processors can also exploit a little bit of data level parallelism, in addition to the task level parallelism that they apparently exploit through threading via vectorized instructions. GPUs, though, are kind of the tool for exploiting data level parallelism. They're optimized for throughput as opposed to latency like a CPU. So GPUs are what are generally used to drive your display in a computer if you have a standalone drive as opposed to a software driver. And how they achieve this is they use much lower clock speeds, but they use thousands of threads to do it. So they're executing much lower number of instructions per thread, but the number of threads makes up for it. It leads to also power efficiency as well. So in order to leverage this computing environment, the tool set we used is CUDA. So NVIDIA CUDA only works with NVIDIA GPUs. And what it is, it's a toolkit that extends C, C++, and Fortran. Our code base is currently about 60,000 lines of C++ code. So this toolkit provided us with the analysis tools that we need to do a deep dive into where the performance issues were currently occurring, as well as do some rapid refactoring and quickly develop on top of it. So it also has very high performance libraries associated, things like Kublas and Magma, which we can take advantage of in our code, which takes away some of the overhead with doing rapid development. So here's a general overview of the algorithm. So the user supplies genotypic and phenotypic information, then that's imported into the system. This is what I said, the 50,000 markers with the 200,000 observations currently. And then we perform Gibbs analysis. Each one of these yellow circles represents one iteration of the Markov chain. Because because you need to have random mixing and the initial state is slightly dependent on your starting state, you need this burn-in period, which is discarded. So that can be anywhere from 1,000 iterations or greater. Then during each one of these states, you are accumulating the mean genetic effect and, along with the prediction of error for each marker. And the end result, you have the effects of markers on the desired trait and an estimate of the error, or the estimated breeding values. So performing an analysis on this code, we found that the most time spent, about 90% of the computation time after reading in the values, was spent in each of these individual links in the markup chain. So this is what the basic Bayes function that we're seeing is being called multiple times. What you're basically doing is computing the probability that each individual marker is included in the model, computing the mean effect, the error variance, and then keeping on going through and adding it to the model or removing it from the model. So this would seem pretty straightforward to optimize, right? You can see you could probably just do each marker independently and just run that. But that doesn't work with the statistical model that we're doing, because the statistical model that we're doing requires you to iterate over the markers in the order that they were given each time. So you actually end up with a sporadic data dependence that occurs in this, where if for each marker that you're going on, if it's included in the model or is included in the previous model but not included in the current model, it changes the state that is used to calculate the mean genetic effect and the error prediction variance for all preceding ones. What we did is in that piece of code, we wanted to identify regions of parallelism that we can exploit. So parallelism exists in a spectrum. There is very coarse-grained on one side and very fine-grained on the other. So very coarse-grained tasks don't require a lot of communication between the tasks. That's well suited to something like a MapReduce job, a distributed cluster. If you need to have if the tasks are more closely related, you need to have some communication between them. CPU threads offer a good way to do that, especially if the code is divergent, in which case you need to be moving back and forth between threads. If you need to apply a common set of methods to a large set of data, but it's a smaller set of SIMD instructions or vectorized instructions offer a good medium for that. But as I said before, if you need to apply one instruction across a large set of data, GPUs are the way to go for that. So luckily for us, after analyzing our tools, the computations we need to perform are pretty tightly correlated. So we really live in these three right here, which is well suited for heterogeneous computing. As CPU threads offered obviously by the CPU, and as long as SIMD instructions, then anything else can be handled by the GPU. So for algorithm optimizations, when we went through and refactored our code and put in our optimizations, we really had a couple goals in mind. We wanted to simultaneously compute on the CPU and GPU as much as possible. So we don't want to have any idle time on the CPU or the GPU, or have either processor waiting for a result from the other. So that means at all times we want to have them both working at full occupancy, exploiting task-level parallelism both on the GPU and the CPU, as well as data-level parallelism. We'll get into that a little bit later. And one other goal is to minimize the idle time. So like as I said, we don't want if there's something that we can be doing to prepare ourselves for future computations, we want to be doing that just to minimize the wait time for each process. So here's the refactored code, just focusing on the right side here for the first part. What we did was we ended up refactoring. This is again what is happening at each link in the Markov chain. We basically split it into two pieces. One piece up here, which is determining if a marker is included in the model or not, and one piece here, which we're actually calculating the error prediction and mean effect. So, as I said before, there's a sporadic data dependence that occurs with it when you're building up that model. So what we did was we divided all the markers into groups, which we call chunks. These chunks are designed to be small enough that the data dependence will not occur in them, or only occur for a subset of them, and try and minimize the amount of basically discarded computation they have to do. Because if we can perform this computation in parallel, right? So we can do it we can be performing it for multiple markers, and then if the data dependence occurs, then all markers after that, all the computation has to be discarded. So if we can minimize the amount of discarded work, but still optimize to take care of doing things at the same time, we basically maximize the throughput. So this first for loop is doing exactly that. For a set of markers, we're running simultaneously this computation to determine if it was included in the statistical model or not. And marker that we encounter that is, or the final marker of the chunk is marked as the terminating marker, and anything after that is marked as invalid. So in this top for loop, there is a chance that there is some wasted computation, but because we're doing it concurrently, it minimizes the impact overall and gives us a performance boost. We experimentally determined the size of the chunk, and in our case, we were running with a chunk size of 6. We'll go over that later in the presentation as well. Jumping down to the bottom part, again, we're just actually including the every marker up until the terminating marker into the model, but there's no wasted computation at this step because we're only going up to that terminating marker. This middle section right here, what we're doing is basically making sure that we're preparing for the next iteration and doing any pre-computing and kicking off and any data computation that we can to pre-compute values that we might need up here. Over on the left-hand side here, you can kind of see the flow through the heterogeneous compute environment. So when we're computing here, a wider line on the left-hand side here with the CPU, that indicates that we're doing multi-threaded, that we're multi-threaded at this point in time. Then during this middle section, we only had one master thread to control things being kicked off on the GPU, things like large matrix computations, which are required for computing this probability, and also any data transfers we need to do between the CPU and the GPU. And the GPU up until here, as we said, we like to pre-compute things, so any computation that we need from the GPU is required at this point. So if there's anything left to be computed, it's computing up until here, again to minimize that wait time. But once we're down here, we know when the terminating marker is, so we know what the next chunks will be, and we can begin computation for the next chunk of data. And here's Trevor to speak about the CUDA side.
Can you hear me? Awesome. Okay, so before we get into the details of our implementation, I first want to go over a couple of the CUDA essentials, which will help get you guys in the state of mind to see kind of why we did why some of our design decisions were made. So first, threads on a GPU, or in CUDA at least, are organized into what's called warps. Those are currently a set of about 32 threads, and each warp is executed in lockstep, meaning that clearly technology is not
It's not high performance now.
Okay, so as I was saying, warps are executed in lockstep, meaning that every thread inside of the warp is executing the same set of instructions. So any divergence in that is gonna hurt you. So we had to try and avoid that. Another thing that's important to know is how streams work in CUDA. So a stream is essentially can be thought of as a pathway to the GPU, sort of. So you can push kernels, which are GPU function calls, down the stream, and they'll be executed in the order you put them into the stream. And you can also take advantage of using multiple streams on a GPU, and the streams can be actually executed concurrently or can be swapped in and out by the GPU depending on what's going on in order to achieve the maximum amount of computing on each GPU. Okay, so next we're going to talk a little bit about parallelizing the dot product, which is essentially the meat of our work. So the size of these dot product computations are scaling with the number of observations, which in our experiments and in the real world data range from about 10,000 observations all the way up to 1 million observations, which is a pretty big vector. It's been proven time and time again that the GPU is capable of computing dot products and other tasks like that much faster than the CPU. The main issues are you lose a lot of that performance in memory transfers if you don't take care of those, and also so additionally, we have another issue, which is memory management on the GPU. So our GPUs only had about 6 gigs of memory on the card, which sounds like a lot, but when you're trying to push over 1 million observation vectors, it ends up taking up a lot of space. So we had to handle that. Okay, so the first thing we did was pipeline our kernel calls. So this is, to do this, we use streams for each observation vector inside of a chunk, which our chunk size was set to 6. We'd open up a different stream to our CUDA card, and then we would send the kernel down each individual stream. And these streams operate asynchronously from the CPU, allowing us to do additional computing on the CPU. And they can be swapped in and out at the GPU's discretion to help maximize the saturation on the GPU. Okay, so in order to handle our memory issue, we couldn't simply move all of our observation vectors onto the GPU, which would give us the highest performance. So instead what we did was we implemented a circular data buffer. So this allowed us to store a set number of observation vectors on the GPU, many more than we would need for any single computation, in order to help minimize the effect of the bus latency. So in this example, for instance, we would have 30 observation vectors stored on the GPU at any one time, and then we'd be only consuming 6 at a time, essentially, for each chunk computation. And then when the next one would come around, the data was already on the card, meaning that we didn't take that memory hit. That memory transfer hit, sorry. Next, we implemented a multi-GPU solution. So to do this, we essentially took our circular data buffers and our stream structures, and we just switched them over and moved them and spread them across, in this case, 3 GPUs, which was what our system had. So as you can see, we also striped the data across the 3 GPUs. So every third observation vector is stored on each GPU. And additionally, this gives us a form of load balancing, because when we go to execute, let's say 6 observation vectors, each GPU is going to be executing to allowing us to evenly distribute the workload. Okay, so this is an example to kind of show how the observation data replacement would work in our circular data buffers. So in this example, our chunk size is 6, so we'd be executing on the first 6 observation vectors, 0 through 5, which are evenly split across the GPUs. And we're going to say that the first 4 observation vectors are actually correct. And the terminating value was within that, meaning that the last 2 observation vectors, 4 and 5, were invalid, so they need to be recomputed again with the updated state information. So as you can see, the first 4 would be consumed, and then they'd be replaced with observation vectors 30 through 33. And then we would start our next computation from 4, which would again give us good load balancing across all 3 GPUs. Okay, so this is our testing environment. We had a pretty good box. We had 2 Intel Xeon processors, 64 gigs of RAM, 3 GPUs, one of which was an NVIDIA Tesla K40, and 2 of which were NVIDIA Tesla K20Xs. And additionally, to test our implementation, we used the original CPU implementation and compared results. Okay. So this shows our end results, essentially for 1,000 to 1,000,000 observations, and then our runs for 500, 1,000, 2,000, 5,000, and 10,000 markers. As you can see, the trend line is pretty similar. Anywhere above 200,000 to 300,000, we're getting improvement over the CPU version, which is to be expected. Anything below that, we just take pretty big memory transfer hits, and it just doesn't, it won't beat out the improved performance from the GPU. So it is important to note that this implementation the implementation we received was inherently sequential, so any sort of speed up that we can get is beneficial. And the CPU version is not a pushover version. Before we were handed the keys to this, the previous developers did everything they possibly could to try and speed up the CPU version. So, it's multi-threaded. They're taking advantage of eigen libraries for computing, and also using vectorized instructions on the CPU, which gives it, pretty good speed bump. But the heterogeneous compute solution is the best, and it provides speed up that an only GPU solution or an only CPU solution could not provide. Okay, so this shows, this is how we tuned for our chunk size. We did it experimentally, so we did a chunk size of 3, 6, 9, 12, 15, and 18. We moved by 3s because we had 3 GPUs, so it makes sense to go by 3s in order to spread the load evenly across all the GPUs. So as you can see, 6 is the best, followed by 3, and then anything above 6 is, they're the worst, mostly because they have the most wasted computation. So for our specific application, that terminating marker comes in low enough that you're wasting a bunch of computation time if you go too high. So this shows our performance for based on how many GPUs we're using, 1, 2, or 3. As you can see, 3 is the best, obviously, that's good. And then 1 or 2 are close. The reason that is that the 1 GPU run was using the NVIDIA K40, which is a better card than the K20s. And therefore the difference between a K40 and a K20 and a K40 is not that big because it's limited to the slowest GPU with the load balancing because it's always going to be an even workload spread. Okay. So this is just a table of our runtimes that shows the number of observations, the CPU and GPU runtimes, as well as the speedups. This was all done for 500 markers, which is the smallest run that we did. And as you can see, just to kind of give you a sense of how long this takes. So with 500 markers, the 1 million run on the CPU takes about 4 hours and 20 minutes, and on the GPU it takes about 2 hours and 45 minutes. So that's about an hour and a half speed up. That's good. But for the real run that they want to do, which is 50,000 markers and 1 million observations, if we extrapolate our results out, the CPU version will take 18 days to complete, and the GPU version will take 11 days to complete. So you save about a week's worth of time there, which is important. Okay, so some acknowledgements. Our research was supported by the USDA National Institute of Food and Agriculture, so we thank them a lot. Are there any questions?
Quick questions.
So sorry if I missed it in your talk, but I've never done any GPU programming, and I'm really curious to know. So if you're doing a computation on the GPU, can you be reading? Can you read and write into that circular buffer at the same time? Like, is it a fully streaming operation, or do you have to?
It depends on the GPU. So you have to have your memory management unit on your CPU has to support it on your motherboard. So it can talk both ways. But then also your GPU has to have 2 streaming multiprocessors, so they can write both ways on the bus. The bus itself is capable, and the toolkit itself is capable, but it depends on the hardware available on the device. So both the K20s and the K40s are compute class cards, which have 2 streaming multiprocessors, which allow for simultaneous read and write both to it, and then computation being performed on that board.
Great.
Okay.
One more question.
Please.
Yes, was there any reason you chose CUDA over OpenCL?
Well, for one reason is just the toolkit that it has. So the other solution, right, is a more general solution. This is tailored around NVIDIA-specific hardware. So it gives us a little bit of a performance boost there, as well as the hardware that we had available. It was NVIDIA, and we are an NVIDIA research institution, so that helped out too. In addition, we find that the toolkit that CUDA provides is superior to that of the other competitors because it gives you, they have very in-depth analysis tools which allow you to really identify where the choke points are in your code and also go into your actual kernel calls and figure out where the occupancy issue there and really do a dissection of your code. So we found that to be a very convincing argument, and also because of it hooks in directly to C++, which, as I mentioned, our code base is about 60,000 lines of C++ code. So because it's an extension of that, we were able to do it very easily.